Let's do an example. Here's a series given as a set of numbers. We need to figure out a formula and then figure out if the sum converges or diverges, and if the sum converges, what does the sum converge to? So take a sec, try to figure out a formula involving n for what's going on here. Pause the video if you didn't, and go do that. Okay, welcome back from pausing. When I did this in a class, some people said maybe it's 0.2 times n over 3 to the n. They picked up that these are powers of 3 in the denominator, and we seem to have something even going on here. But if it was 0.2 to the n, it would go 0.2 times n. It would be 0.2, 0.4, 0.6, 0.8, 0.10, well, 0.10, 1.0, something like that. But we're missing the 0.6, so this seems to be more like powers of 2, 2, 4, 8, 16, but there's a decimal point there. So we'll say, nope, it's not that. Is it 0.2 to the n over 3 to the n? Think about that. Well, 0.2 to the 1 would be 0.2. 0.2 squared would be 0.04. And 0.2 cubed would be 0.008. We'd be getting smaller. We'd like have 20% remaining of what we used to have each time. So that would be getting smaller each step instead of getting larger each step. So it's not 0.2 to the n. If this was just 2, 4, 8, 16, that would be 2 to the n. So we could write 2 to the n over 3 to the n. But this is 1/10 as big as 2, 1/10 as big as 4, 1/10 as big as 8, and 1/10 as big as 16. It's like we just moved the decimal place 1 over. So we could say it's 1/10 times 2 to the n. So let's say our sum is the sum of 1/10 times 2 to the n over 3 to the n. Is this starting at n equals 1 or n equals 0? Take a sec to think about that. Well, to get 3 to the n starting at 3, we need n to be 1 to begin with. So it would be that. Is this a geometric series? That's a good question. Geometric series has r to the n. Let's remind ourselves what geometric series is. The sum of r to the n. It doesn't allow for a constant here. Can we do anything about that? Well, we could move the constant out front. So say 1/10 sum n equals 1 to infinity. And then we can rewrite 2 to the n over 3 to the n as 2/3 to the n. So this is seeming to say that r would be equal to 2/3. That's a constant that we're raising to the n. And what do we notice about 2/3? The absolute value of r is less than 1, so the sum converges. So that's pretty nice. We turned a set of numbers into something that we recognize as a geometric series, and even figured out that the sum converges. What else can we do about it? Well, before we go on, let's think of another way to see that it's a geometric sum. That it doesn't even depend on like moving the 1/10 out or realizing that the 1/10 is even there. Let's take the second term here, 0.4 over 9, and divide by the first term, which was 0.2 over 3. If you do all that arithmetic, another way to think of it is the denominator here becomes the denominator there, and the denominator here becomes the numerator in the denominator, and you get that top is 2 and the bottom here is 3. Kind of interesting. Let's try the next one. Let's try 0.8 over 27 divided by 0.4 over 9. So go ahead and do some arithmetic on that. You can still say 0.8 divided by 0.4 over 27 over 9. 0.8 over 0.4 is 2. And 27 over 9 is 3. Amazing. So one way to think about a geometric series is that if you take the ratio of successive terms, like a sub n over a sub n minus 1, or a sub n plus 1 over a sub n, then that ratio stays constant. I mean, we only tried it for 2 things here, but it seems like a pretty good pattern we can trust based on the numbers we were seeing. And the constant you get is the r value. So r is like r to the 1 over r to the 0. That's the ratio of the 0th term to the first term, or r to the 2 over r to the 1, or r to the 3 over r to the 2. So this is successive terms in the sequence. So that's a quick way to discover whether a series is geometric. Take this ratio of successive terms, and that has interesting links to a whole bunch of other stuff like exponential growth, exponential decay. So that's a quick way to think about things, and if it works, you get the r value right there. We wouldn't have discovered the 1/10 this way, but at least it's a way to discover the r value without having to think about all that 1/10 stuff. Let's go find what the sum actually converges to, since we found that the sum converges. Well, we know that the geometric series starting at 0 is 1 over 1 minus r if the absolute value of r is less than 1, which it is in this problem. It's 2/3. What do we get there? We get 1 over 1 minus 2/3, which is 1 over 1 minus 1 over 1/3, which is 3. So can we say that this sum converges to 3? Well, there's 2 problems. This sum starts at 0 rather than n equals 1, and we had a 1/10 out front. The 1/10 out front we can take care of later. What can we say about, so that n equals 0 is equal to r to the 0 plus the sum n equals 1 to infinity, right? Just breaking out that 0th term. And so to get this all by itself, which is what we want, we can say minus r to the 0 plus the sum starting at 0 is the sum starting at 1. And then now we want 1/10 of that, so let's multiply this whole thing by 1/10. So that's the number we want. We know this infinite sum was 3. We know r to the 0, well, r is 2/3, but anything to the 0 is 1. So we have a -1 there, and 1/10. So that's our answer. So here's a question: how do we check that? We expect the answer to be positive, right? Because we're adding only positive things. Is this indeed positive? Well, 3 plus -1 is 2, so overall we get 2/10. So that's positive, so that's a good first check. We could type our summation, this summation or that one, into Wolfram Alpha, and in the homework I show the format for typing that in. So hopefully that would give us the right answer. But that would depend on us getting this summation correct. We could actually just type the first few terms of this into a calculator or into Excel without doing all the end stuff, but just literally type these numbers, and we should get an answer less than our true answer because we're leaving off some positive terms here. So if the series is converging fairly quickly, then this sum of just these first 4 terms would be pretty close to our final answer, so that's another good way to check.